again. All right, so the recorder, oh, I actually can see what's wrong. I have two lesson 12s, so that lesson 12 must be 13. That would mean this lesson 13 is really 14 or 15, and then 15 is really 15 or 16. There's links to I think everything. I may have the numbering incorrect, but that's all that's there. So that'll be available by the end of tonight, and I'll get tonight's uploaded probably without very much narrative here. Okay. See, I'm going to just shrink that because it used to be if you disconnected, it would destroy all your work because that was their way of telling you that they really loved you. And I'm going to put you guys over here. Everybody's here. And we will go through what I had intended for tonight. So I tried to formalize the ICPR that I introduced at the end of last time. And so here it is all in writing. So that must make it better. And it's on the internet, so it's got to be right. So what we are segueing into now is what I've entitled the ICPR concept to approximate two-dimensional overland flows, and we're using SWMM. So ICPR is an acronym for Interconnected Pond Routing, and it's both a concept and it's also a particular branded software, and we'll go visit the brand. So the company is called Streamline Technologies. It used to be called something else, but software companies change their name every time it looks like a lawsuit's going to catch them. So this is a background of ICPR, and this was built originally in Florida, I'm pretty sure, and it started out as this leftmost picture, which we have explored fairly extensively in this class. And if you had water systems designed from me, you saw it introduced there, although you probably didn't know it. And they discussed their 35 years of history, and then they've added their version of 2D overland flow component, which my opinion is the way they added it was unnecessarily complicated if I had to program it, but it works for them and they've done all the work. And then they've had 2D groundwater connections were actually always available with some cleverness. And you can look at their product literature at your leisure. If you had to do this for real and you worked at a company that had a license to use ICPR, I would go ahead and use the tool. It is a robust and reasonably good tool. So the concept itself that's implemented in the branded software, as well as how I'm going to illustrate how I've implemented it in SWMM, the concept's remarkably simplistic, but it's quite useful. So so you've seen these words already because I just showed you the corporate website, and I literally stole it directly, because if you're having to make a written material, it's easier to steal than it is to create yourself. They say that that talent creates ingenious steals. So I'm a genius in this moment. What we do is we're going to logically extend the ICPR description from the corporate website. And in my opinion, a logical extension of the idea itself is that the ponds themselves don't have to be large, and they don't necessarily have to be real things that you can identify. I mean, there is an aspect of reality involved, otherwise there's no point in doing this. We should go to Hollywood and do real modeling. If we can conceptualize our problem domain into small cells, and then we assign each of those cells a storage property, and then connect those cells with links that represent plausible flow paths overland. Then a program like SWMM can actually handle the required hydraulics to keep track of the flows, the flow directions, and more importantly, the water surface elevations. And once conceptualized, the computational problem itself simply becomes a network of conduits and storage nodes. And while that network is not trivial to solve, it's well within our capabilities of writing our own code if we have to, or using SWMM to do it. Once you recognize that we're creating a conduit of network and storage nodes, the remainder of the concept is fairly straightforward. There's three primary building blocks that get used. Ordinary nodes, which we won't really talk about much today, but I will illustrate in a case study where they play a role. Links or conduits, as we have already conceptualized them, and storage nodes. Another building block that I don't have listed is the subcatchment, which is the hydrologic portion of the integrated hydrology hydraulics. So we tend to do these ICPR or actual two-dimensional flow when we're trying to integrate hydrologic response over an area with a hydraulic network, and we're interested in asking questions of our model at locations that are not easily interrogated using conventional or older one-dimensional hydrologic concepts. And we have a picture coming up that'll make some sense. The resulting computational framework is simply a link node model. The storage nodes are placed, it says at strategic locations, at prescribed locations in the drainage network. We calculate water elevation at the nodes based on inflows, outflows, and the node storage characteristics. Waters move from node to node via links such as pipes, channels, weirs, pumps, bridges, and dynamic wave routing is the usual tool for the channel and pipe flow. The older one-dimensional approach that we're accustomed to and have likely had in other classes, and this picture should look remarkably familiar because it's the same watershed that I drew last time, is we take our study area and we would examine mostly the topographic consideration, and we use that to identify drainage basins, subcatchments. In the drawing that's depicted here on your screen, there's three. There's subcatchment A, B, and C. So subcatchment A corresponds to this entire area. B is this area, and then C corresponds to this triangular area. And then generally we would use our hydrologic analysis to convert all the rainfall on area A into some runoff. And then we'd probably have a unit hydrograph associated with areas A, B, and C. And that rainfall runoff conversion and then the unit hydrograph is used to put flows into our network somewhere along this tributary. And once it's in the tributary, then we do ordinary hydraulics. Same for B, and then C might be taken all the way to the larger basin outlet or somewhere intermediate. And then hydraulic routing occurs in these channels. And our older approach generally is aimed at determining discharge and flow depths at that point, or perhaps any point along the identifiable channel. But the old approach is completely inadequate if I'm interested in a flow depth right where the cursor is. So the cursor's moving, making you nauseous. I don't know how fast it's moving in network world. And if we're interested in the water depth right there, our old isn't the right word and classic isn't the right word, but what predates the distributed approach is, for all practical purposes, is incapable of making an estimate of flow depth where the pointer is. So the alternatives prior to going to distributed modeling is to get all the water into the channel, and we'll just calculate the top width relative to the channel. But that's arguably absurd when you get somewhat far away from the main channel. If the distance from this point where the cursor is to midway into that watershed is 2,000 or 3,000 feet, it's pretty ridiculous to think that the channel width at that point channel top width could possibly give us a reasonable estimate of flow depth. In fact, I would argue that if it shows any water there, we got bigger worries. So the ICPR approach at its extreme, and the way I've implemented it in the past, and we'll show a case study shortly, is to superimpose a relatively small grid over the study area. So here you can see actually an extraordinarily small grid superimposed on the study area. I drew the grid before I realized how hard it was going to draw the flow paths. And then we declare each grid cell to be its own subcatchment. So we get no advantage there whatsoever, except that we have a whole lot more subcatchments to deal with. One could argue that because these subcatchments are smaller, it might allow us to do a finer grained hydrologic discretization, but we're paying a pretty big cost to do that. But each cell is also declared to be a storage node, and we could apply glass walls as necessary, and I'll show a drawing of what that means coming up shortly. And we construct it in our computer program so that flow can only exit the cell through links that we provide, either overland irregular channel shapes or underground pipes, or a combination of the two. And in doing that, we're able to directly incorporate topographic information, either as a max depth above an invert elevation or some offset from that value. And that allows us to capture the topographic drive of the two-dimensional overland flow component. We still retain whatever model we've built of the actual channels. There's often a little challenge in describing the cells that live along the actual channel, but it's not insurmountable. And in doing that, what we do is we are transferring more hydraulic behavior to the individual storage nodes or storage cells, such that if the question we want to ask of our modeling world is what is the flow depth at some location in the interior of this grid system, that's an accessible answer to recover. We go to the correct cell and we have it report back the computed flow depth. And that would be a much more reasonable tool for determining things like what's inundated and what's not. Now, the SWMM program that I'm using and have discussed for this class, computationally, it has no trouble with this. But the EPA supplied program, the graphical interface, is pretty terrible at providing us nice mapping outputs. And so that sadly is something we would have to do ourselves. We could use our Jupyter Hub, our Jupyter Lab notebooks, and spend a lot of time on the internet downloading and getting mapping tools in Python to work. They're readily available. That, other than that, taking some time and a little bit of thinking effort, that's not difficult at all. Naturally, I've not done it, so but that's not that difficult. And then we would have to take our SWMM model, and instead of having it write output to pretty drawing things built within the computer interface itself, We save that output as a file, and our Python script has to parse the file and construct it so that we can make pretty pictures. We're not going to do that today, or probably not this semester, but that would be the hard activity of doing this. But what we get at the end is an entirely hydraulic model that can estimate water depths anywhere in the study area, not just the channels. There's quite a bit of art required to do it in SWM, in EPA supplied SWM. Or if you're lucky and you work at a company where they've bought a product from a value-added vendor, they supply tools that automate a lot of the art. So for example, this is a product by a company called Bentley, and it does really cool, pretty graphics and things like, ooh, that's like really simulating the flooding in the streets. Underneath this cool picture is an elaborate SWM type model that's keeping track of what the flow depths are at nodes, and this is just joining the depths at the nodes together, superimposing pictures of cars, red brick buildings, and whatnot, in order to make scary pictures to help convert public money to engineering projects. So that's one example of their product, and they have a few more. This is actually a pretty good company. As a business, they're a horrible business. Their business ethics are certainly at times questionable, but their products are well thought out, reliable, and if you're paying enough money, you get really good support from the company. I do not have a business interest in Bentley, other than occasional rough arguments with some people that work there. But I can't argue with the end product because they steal it from the best people in the world. They're true geniuses. Remember, genius steals, talent just creates. So let's look at a way of trying to conceptualize this interconnected routing model. Here on the figure, I've drawn 3 nodes, and what I'm attempting to imply is that there is an axis moving in this direction, and then there's an axis moving this direction. So if you could move your head looking down from the top, this would be a backwards L-shaped topology of these 3 rectangular nodes. So here's node 1, and there's a surface link between node 1 and node 2 indicated by this red dashed line. This is node 2, which is kind of in the center of the drawing, and there's a surface link connecting node 2 and node 3 to one another. And then here's another surface link going somewhere, and there's no node here. You'll have to mentally supply the all the other nodes that are around here. So again, think of it as a dense collection of these rectangular bathtubs. Above each one, I've drawn a picture, also a rectangle called subcatchment. This one's subcatchment 1 that associates with node 1. Subcatchment 2 associates with node 2. And subcatchment 3 associates with node 3. The subcatchments are features that are already in our SWM program, and their main purpose in life for this discussion is that they give us the ability to convert rainfall into a runoff component. And that which is not runoff, unless we do otherwise, just becomes loss. There are ways to keep track of that loss and return it back to the system. I'm not going to talk about that anytime soon. So for the time being, it's just loss. So if there's perhaps 1 inch an hour of rainfall comes in, and one of these subcatchments is an acre, the expected runoff, if there's perfect conversion of that rainfall into runoff, would be a cubic feet per second would eventually come off that drainage area. And that would scale directly proportional to the area and proportional to the fraction of rain that gets converted to runoff. So what I just did in my head was a rational equation because that's why it's very popular, because it's really easy, but also really wrong in many instances. There are other models available to convert rainfall into runoff. So let's test everybody's long-term memory. Who can suggest another model that's in common use that converts rainfall into runoff? Oh, awkward silence.
Like a program that converts that, or I'm sorry, it was.
Yeah, a method, something that converts rainfall into runoff. So I stated rational method, and I just did it in my head, which, interestingly enough, is not directly in SWM. You have to finesse a rational method. But what are some of the other ways that you learned in hydrology to make rainfall into runoff? If you can even tell me the parameter, I'll go ahead and let you have that.
Isn't Hazen Williams one? Or am I mixing them up?
They're mixing up. Hazen Williams is a loss model for pipe flow.
That's what that is. Okay.
So Anna looks like she knows an answer, but just doesn't trust herself to risk it. And she's muted and talking. Perfect.
I pretty much, but I just no, I rather not.
Richard, do you have any ideas?
No.
No? Okay. Jawad? Oh, I'm embarrassed for y'all. What about the NRCS curve number method? That converts rainfall into runoff. What about the one that involves a color, green amped? That's a way to convert rainfall into runoff. So anyway, those particular, oh, and my favorite one, because it was the guy who heard a who, there's Horton's method and modified Horton's method. And then there's the Dunn, let's see, infiltration. There's the Dunn saturation excess method. So anyway, there's quite a few models in the literature that provide a mechanism for us to computationally determine what the anticipated runoff is from a unit of rainfall on a subcatchment. So this dashed rectangle either implements, in the case of SWM, curve number, Horton, or green amped, or variations thereof. And although it's often criticized as a limitation of the program because it doesn't do every whiz-bang model that there is, an ingenious analyst can use the three models within it, and in many cases simulate not any, but almost any of the ones in the literature. For instance, you can approximate a rational method simply by using a Hortonian model and putting a couple of absurd numbers in the initial infiltration and the asymptotic rate to guarantee that all your rain would become runoff, and then use the fraction of impervious as a runoff coefficient. It's a hack. It'll work correctly, but it's a total hack. But again, a good analyst can hack any rainfall runoff model that they're likely to need. So let's stipulate that part of the tool is available to us, and nobody's going to tell us how to use it. That's going to be on us. So now we can get these runoffs, and they go into each of these boxes. And if there were no surface links, we generally build these boxes conceptually in our computer program that if runoff is coming in, the water level's got to go up. This depth value's got to get bigger because we're filling up the bathtubs. And then we connect the bathtubs. For example, bathtub node 3 to bathtub node 2 is connected by this link. And then that link has cross-sectional geometry properties, has a Manning's N, and in the extreme case, the length of that link corresponds to the distance between the centroid of node 3 and the centroid of node 2. So you can visualize node 2 and node 3 as butted up next to each other. We can't see this dashed red line. Same for node 1 and node 2. And we use the dashed line conduit to provide a mechanistic way for water to get from node 1 to node 2, but it has to make that transition according to the hydraulics that are forced on it by the geometry of the surface link. So taking that a little further, if we're looking at one of these node edges, let's look at this one. And I'm going to put my eyeball where node 3 is. I'm going to look back towards node 2. And I'm going to look at it in elevation view. So I'm going to see this face of node 2 that I'm drawing with the cursor. And there's what I see. I see this node 2 edge or node 2 face. And I have superimposed a cross-sectional geometry. And here I've just drawn it. And so the resistance to flow between adjacent nodes is determined by the length of that link, the cross-sectional geometry in Manning's N, and then to force it not to do entirely ridiculous things, we often do glass walls. So those are these vertical lines showing here. So what that will do is that forces the water to have to go through this link or any other links from the nodes rather than leaking over the edge. Because again, remember, SWM was never originally designed to do a quasi two-dimensional flow. I'm showing you how to trick it. We can extract aspects of the node storage properties either directly from a topographic map. So if we have a node that we're really comfortable on flow path and we know it's going to flow from this bottom edge to the top edge and there's no realistic way for it to go horizontally, we can quasi superimpose a topographic map. And what this picture is showing the fraction of the node that would be inundated for different depths above the node bottom. So the +1 line would be this area right in here. And if the water got to be 2 units deep, it would be that area right there. And then here we have these glass walls. A more useful way to conceptualize a node, in my opinion, and I'm the only person in the history of the world that's ever used, that recognized you could use SWM this way a long time ago. I'm not the only one that ever did it. Is what I call generalized node storage element. And this is hard to mentally visualize. It's easy if I build a physical model, but I don't happen to have one handy. When I get my 3D printer up and running correctly, I will print a node so I can show that in the camera and it'll make more sense. But we're looking down on this node. So at the center of the node, we declare that the most bottomness of the node, and then it's ramping up from the center to the corners. And so what that does is it builds these little steps as I've drawn it. So for example, if the water depth in the node is 0, there's no storage. There's no area associated with that. If we let the water depth get to 1 unit, it makes this little cross sign right here that I'm wiggling on. If we get to 2 units, the cross gets bigger. If we get to 5 units, the cross is huge relative to the node shape. And so if our eyeball's looking on this edge, the optic nerve connects it to this sorry-looking brain, which visualizes what it sees on that edge is a shape that looks something like depicted here in the drawing. And what this has is, if you put 4 of these nodes together, you have pyramids connected to one another. This corner here is the top of a pyramid. And so you're representing your whole surface as a collection of pyramids where the space between adjacent pyramids is where we attempt to capture topographically correct elevations. So it's modeling the Earth as kind of a rough collection of pyramids, but the node centroids are assigned the correct topographic elevation. So what we gain for the pyramid is all flow models, whether it's this one or something fancy that uses actual calculus and the mechanical engineers put on wizard hats and charge a lot per hour to run it for you. They all have to have connectivity. A Eulerian-based water flow program doesn't function very well if there is not some path from node 1 to node 2, node 2 to node 3 that's actually achievable. So what this collection of pyramids does is it guarantees there's a flow path from the centroid of every node in the model. Unless, of course, you have a node that is lower than the eight nodes around it, then water can't get out until it gets deep enough. So that's a trick that I've implemented in my representations. It's hard to visualize. This is something that would be really good if you were in a client meeting, to have a small, like I said, 3D printed model of a collection of about 15 or 20 nodes, so you could show your clients where water flows in your computer model and where it's stored when you're calculating inundation. And I'm pretty positive that the Bentley software and the ICPR-4 software does a trick like this, and they probably don't bother to tell you because they don't want to have to attempt to explain it, just like I'm struggling. Lastly, we can also directly incorporate sewers as simply another link. So there's a subsurface sewer link. Here's our surface link. And when we get to this situation, we actually have a pretty complicated elevation model, because the bottom of the sewer would be where we would establish an invert elevation, and everything gets measured from that. We have an offset to get up to the land surface, and then we have to have a maximum depth to allow water to get above the land surface. And so these take some fairly challenging Python scripting if you take the files out of SWM and you're trying to show where the land surface is and then water above the land surface. It's not impossible, but it's fairly tricky. The rest of today's lesson are these pictures associated with subcatchments, precipitation losses, surface length, and it's obvious I didn't get all that created yet. So let's, there we go. Let's take a look at a couple of case studies. Let me get one of them finished. Okay, everything's on the server. If you had water systems from me, you've seen these before, but you remember that was around lesson 24 of water systems, and by then you had severe everything fatigue. And so, and I went through them pretty quickly. I'll take a little bit more time now because literally it more appropriately fits this class. So that's my bad. We have to go to my friend at Anaconda and log in yet again today. To F in 457. Wish I could say that like Swin Pickens. 2FR in 457. Can't mess around with the password because my finger remembers it better than my brain does. So I'm going to just go ahead and load up and get my swim running, and I will grab 2 case study files and we'll take a look at them, and we'll go through them a little bit, one piece at a time. Won't cost me a dime. Got a 59, 61, 60. I have a Johnny Cash song playing in my head right now. I'm going to try to get that out. Spinning circle. Okay, good. That's what we wanted. Being obstinate right now. There we go. I hope I saved stuff to the right location. There we go. So lesson 17 is correct, and I had to get to it by going to lesson 18 because I can't count. I'm going to download 2 case studies. And I'm going to see if it actually will let me grab a whole. I don't think it'll let me take a whole directory. Let's give it a try. Yeah, that's all screwed up. So I actually have to go in it. I need the input file. Save link as. Let me actually change it. So WODLANDS ditch C. And I'm going to get another one where we have a relief sewer, and then I will go play with the programs. And I'm saving us the thrill of having to convert topographic data into a swim model and so forth. That's been done. Okay, I don't think I need my Firefox up right now. We'll take this first case, open it up. Got to go find the base map, and then I'll undo the base map. Okay, so like I said, if you've had that other class from me before, you've seen this, but it was done late in the semester. Everyone was fatigued, and your brain, as a protective mechanism, ignores everything I'm saying, and that's fine. That's completely human nature. So here is an example of a study area. It's at Gosling Road and Woodlands Drive. This blue object is called is a drainage ditch, affectionately known as Woodlands Ditch C, although Ditch C is actually down here. And the topography of this 300-ish acre area, so that's half a square mile. Not large in the world of drainage modeling, but not minuscule either. Interestingly enough, actually has legitimately defendable hydrologic boundaries as indicated by the map. And a grid system has been superimposed, and the square red boxes represent the grid cells, and as I recall, they're 1.3, I think they're 1.3 or 1.6 acre boxes. And so this is what I meant in the written part by a reasonably dense grid. Doing these grid cells on the order of a few hundred feet by a few hundred feet kind of defeats the ICPR model thinking. At that point, we're in a different type of world. But here we can approximate things at a useful scale. 1.6 acre cells gives us the ability to estimate average flow depth in a cell and declare whether or not that cell is flooded relative to the structures, in this case, residences that are located within the cell. These streets have a curb and gutter construction, and generally 6 to 8 inches of water in the street or in any one of these cells would not be considered flooded, although it would certainly be difficult to drive your Mercedes quickly through there or my neighbor's go-fast car. And then anything above 1 foot is declared flooding for the purposes of this particular study from a while ago. So let me turn off the backdrop and let's explore the model that somebody has already kindly built for us. So there's a model, and it's admittedly complicated. We can see the north-south, east-west grid structure of our model drainage network. We have these oddball-looking things right here and right here that are going clearly not in a north-south pattern. And if it mattered, you would put some effort into making everything line up all pretty, but it's not really necessary to operate the model. Each of these black rectangles is a subcatchment, ingeniously named by whatever naming convention is built into the computer program. However, this was a model done for real, but it was, again, a prototype thing, so we didn't get to the trouble to actually name the subcatchments. we probably would have named them based on the intersection of the streets at the centroid of the cell. That would make sense for this location. But for time being, subcatchment 147. And if we look at subcatchment 147, its area is 1.77 acres. So that's what the cell size is. And if it converts rainfall to runoff, that runoff is sent to node 57. And node 57 is going to correspond to this storage unit. Let me go back to the subcatchment. And so the subcatchment is where we perform a large part of the hydrology. The X and Y coordinate are simply how it's drawn on its own coordinate system. It receives input from an object called rain gauge 1. Again, extremely creative naming in this case study. More likely, had it gone to a full production run, the rain gauge would have, can't remember what, it would have been 057, and then there'd be 6 more digits to identify the gauge ID. Outlet 57, this particular catchment is set at 278 feet wide. If we were to take 1.77 acres, multiply that by 43,560 to get it into square feet, and then take the square root of that number, I bet it would be pretty darn close to 278, because that's how this was conceptualized when we built it. The watershed has an arbitrary percent slope of 0.5, so 0.5%. That's reasonably flat. There's a percent impervious set at 30%. The Manning's end on the impervious portion. You can read the SWMM documentation to see what each of these means. And then we have percent zero impervious is set at 100. These get overridden by the green amped model that's used in this study. In this case, there's no loss to groundwater. There's no low impact development controls, land uses. There's nothing special about them. There's no buildup, curb length. So there's a lot of features that you can build into a storage element that are not activated in this particular example. And that's fairly typical of any real model that you would ever be involved with. You won't use all the features. So in this case, the infiltration method is a green amp method, and it's set with an initial soil moisture of 65% saturation, so 35% deficit. And the suction head is 3.5 inches, and the hydraulic conductivity at saturation is 0.5. It's going to be inches per hour. So it's a standard green amp model, and that is well documented in the literature. And so this is I consider this particular type of model a pseudo soil physics model. And I don't mean pseudo in a critically bad way, or not like they're trying to cheat anybody. Soil physics is an incredibly complicated topic. The governing one-dimensional model in common use is called Richard's equation, and the green amp is a simplified solution to the Richard's equation. So it's treating the surface that contacts the bottom of this storage element as a sponge with very well-known physical properties, and they're listed here. And so what this model will do is, as rainfall comes in to that subcatchment, a certain portion will go to satisfy this deficit until the soil is saturated, and then any beyond that value becomes available for runoff. The rainfall rate once the thing is fully saturated, has to satisfy this hydraulic conductivity. So it will only produce runoff when the rainfall rate for a computation interval is bigger than 0.5. I'm pretty sure this is in inches per hour because this is in Montgomery County and we don't use the SI system in the United States because we're special and arrogant, I guess. Special. I'm going to go with special. Once the dollar is sufficiently devalued, we'll switch to the metric system overnight. Your guys' heads will spin when that happens. It'll be funny. So that converts our rainfall into runoff. Here is a rain gauge, and we'll look at the time series. So it's a 6-hour rainfall period, and it's pretty boring until about a little bit before hour 4, and then it gets clobbered with 15 inches an hour for 15 minutes and then declines. So this is a 100-year annual recurrence interval, 6-hour rainfall event that has then been deconvolved to have this rather peculiar storm center at hour 4. That's clearly a design storm. That's not necessarily a real event. And there's other options in the time series. So that's our rainfall input. And oh, that's interesting. It claims that is cumulative. Huh. That is not a cumulative time series. I may have to change that. That is, let's see if those are intensities. 5.5. It looks like it's accumulating up to something goofing going on here because this is, those have to be incremental. Go ahead and switch that to the correct type of input. I'm going to assume it's intensity first and we'll see what happens. Can't break anything. That's the beauty of it. Okay, so we've examined a subcatchment. Let's just examine a storage unit. We'll go to storage unit. What was the one we were at? We were at 147. We'll go to the storage unit 57. So the storage unit has an invert elevation of 149.25 feet. Maximum depth is set at 20. And it's a standard storage curve. And if we look at the curve, it's not very interesting. Remember, that picture? And I'm going to go show you the storage curve for the simulation. Except now I've lost it. Okay. Damn it, where'd you put it? There it is. So that's where that storage curve shape kind of comes from, is that conceptualization. And in the case of a standard storage curve, you can think of it as a square where the corners are filled, and each corner represents 1/4 of a pyramid. And it's not a very interesting, this is kind of a goofy pyramid because it sort of changes slope as you go up the pyramid. And that's sort of, it does change slope as you go up the pyramid. And the input is depth above the bottom of the storage unit, and the area associated with the pool that's formed at that depth. So at 5 feet deep, we're at full 1.77 acres, and I'm going to guess that 1.77 multiplied by 43,560 produces a number relatively close to 77,101. Because if it doesn't, then I'm wrong. So we've seen that before earlier this semester, as well as any other time you may have used SWM. Invert elevation, the max depth is to be sure that we can actually store water in it. And unless otherwise specified, the invert elevation represents the bottom of this storage unit. Let's look at, we'll look at the north-south conduit that's connecting this storage unit 57 to storage unit 49. So the conduit is also set to have a maximum depth of 10 feet. The length is 278 feet, which is likely equal to the square root of 1.77 times 43,560 divided by 2 and then times 2. So that number, and that's representing the distance between the centroid of one storage unit and the centroid of the next storage unit. And if we go and look at the cross section, this is called a backyard transect. There are others that are available in this particular model. There's a natural tree section, backyard, street ditch, drainage ditch, line ditch. So if we look at what a backyard section looks like, there's a screw up in the data file because that's a street cross section. Oh, that is a street cross section. So the transect is all messed up. We'll go street and ditch section. Okay, that's what a street and ditch section is supposed to look like, so I'm fine with that. I have a feeling that my model got broken at some point. That's not how I recall we conceptualized a backyard. So at some point in the numerous copies of these input files from one place to another, the backyard transect got broken. But the point of the discussion being is we represent the connections between two adjacent cells. In this case, the analyst decided that those two connecting cells were connected mostly by a backyard type connection. That's described in the report. Let's see what other choice we have. Street section like woods. Oh, okay, I get it. At some point, the analyst, which would be me or Will Buckins, who was working for me at the time we did this, decided that the street section with light woods was a more appropriate for that connection. We never changed the transect name. I sure hope we did it right in the final report. So actually, that's a good learning lesson, what I just said there. I sure hope we did it right in the final report. These models end up being pretty complex, and the QA/QC part, you need to schedule a day or two to go through what you're going to consider your production model. And not alone, you need another set of eyes in there to ask the questions like, well, why is that called a backyard that looks like it has a street in it? And then you can go run down whether that's an error that creeped in or an oversight and correct it for your final product. So that's one of the connections. So if we look at this other connection, conduit 35 is the same kind of a cross section. So we've examined the storage, we've examined a conduit. Let's go to this funny looking object right here. Actually, I want to go up to this part, and that's a irregular section. It's now miraculously 400 feet long. If you recall from the picture, it's not obviously connecting any two storage elements, and it's called a drainage ditch. And if we examine the geometry of the drainage ditch, it has a very different geometry than our backyard section. Notice the drainage ditch is about 7 feet deep before it comes into an overbank section that looks anything like our overland flow. So when there's a drainage ditch, it's actually just what it says. That is a channelized cross section. And in that particular location that I selected, it's not directly passing through a storage unit. Instead, there is a connection. Oh, you're gonna make me do it this way. There's a connection from the storage unit into the drainage ditch, and most likely this is a pipe. It's a trapezoidal channel that's carrying water into that drainage ditch. So I would suspect that on the aerial imagery, there is an obvious connector there. Down here, this is also a drainage ditch, but that does indeed pass through one of our storage cells. So let's look at this particular storage unit, because in that case, the invert elevation is adjusted to reflect that there's an 8-foot ditch passing through it. The reason being is we need to measure from the bottom of that 8-foot ditch up to the land surface to get our inundation calculations correct. So in my experience, that's the most difficult thing of using SWM, or even the fancier models with good interfaces, of getting right, because a single elevation error in one of the storage nodes completely screws up the performance of the model, and sometimes you don't notice it immediately. And you spend a lot of time modeling and then proposing engineering changes, and then you realize you have a single elevation error. It's usually not a big deal to go back and fix everything at that point, but it's a monumentally frustrating pain in the butt, and a kill a day. So here's our drainage ditch, and then let's look at what this is. I think this is, okay, those are pipes. That was what I was looking for. So this particular subdivision does have a small portion of sewer pipe, 2-foot diameter, and there's no inlet or outlet offset, so the elevations of the connecting nodes have been adjusted to put them underground. So this model actually has all the pieces in my picture show. Those pipes are conceptualized in this fashion in locations where there's a surface link and a subsurface link. And you notice the model actually did a fairly clever trick and intentionally moved the pipes off of the grid system axis so that they could find them in the future when the client asks questions about them, and then connected the storage unit into the subsurface with a 1-foot lateral connection. So let's see if this makes hydraulic sense. I will zoom in again. That's probably a good scale right there. So let's look at this storage unit. Its invert elevation is 142.75 feet. The storage unit relatively north of it is 146 feet. So there's a 4-foot drop from the bottom of this storage unit to this storage unit. So this overland flow connection would suggest that if water pools up here, it's going to want to flow in this direction down here. The bottom of the sewer is at 135 feet. So the sewer is clearly underground relative to this location. So any water in here is going to want to go into that sewer before it goes to the west, which is at 142 feet, or to the south, which is 146 feet, or to the north, which is also 146, and this is a low spot. So here we have a low spot, which now tells me why that sewer was installed there when it was originally built out. Because low spots are notoriously difficult to drain by overland flow, because that would require the water to go uphill. The only way to make water go uphill is to take piles of cash and throw it at the water, and the water will eat it up, and then it will go anywhere you tell it. That pile of cash in this case is manifest as a 2-foot diameter sewer that's buried underground. All right, well, let me run the simulation. And these types of simulation models take a fair amount of time to run. So we're on day 3, 4, 5. I don't know how many days is it supposed to run. And I did change the type of rain data, so I may have broken it and not known it. Okay, so we're done. Let's go ahead and use the map. We're going to take the nodes. We're going to put flow depth, and this is a non-routine coloring scheme. So I suspect that a flow depth of anything over 1 foot, we'll see that as a color change. And if the flow depth gets over 20 feet, we'll get red. Now keep in mind, these sewers are underground at least 10 feet. So these don't become a concern until we get red values in the surface nodes. And I'm intentionally stepping through this one at a time. So you see the drainage ditch nodes are starting to fill up, but water that's between 1 foot and 5 foot deep in a 7-foot deep channel is not a concern. That's what I mean by the swim interface is not the greatest for showing the results of this. And here we have this particular sewer is probably full of water. These are 2-foot diameter sewers, so if it's showing a flow depth of 5 feet, these are definitely surcharged sewers. And we have between 1 and 5 feet depth up here in the north part of the subdivision. So this light blue is now, think of it as flooded. And then the system drains. Let me get down here because I don't want the blinking on one of our interior cells. We go to the next day, and I don't think anything interesting happens in the following day. So let me go back to the first day. I'll speed the animator up and let it go through everything all by itself. Hopefully the days are changing. Should go to 1.4. Okay, so the only cell of interest of concern is storage unit 48, where the flow depth gets well above our 1 foot criterion, and we could actually generate a time series, and that particular cell goes well over 2 feet and stays there indefinitely. So what the program has just identified is a low spot in our drainage network. We can verify it's a low spot by, actually let me do it this way. Let me get node, I think invert gives me the invert elevation, but a useless form of information, so never mind. We'll have to do it with the, that is invert elevation of 133 feet. So I suspect that all 8 nodes around it are bigger than 133. That's 149, which is bigger than 133. One 46, 142, 139, 136, 146, 149, 149, and our target was 133. Yep, this poor cell is a low spot surrounded by tall buildings. In our ICPR quasi 2D model that we just built, there's no way for water to get out of that cell other than evaporating or infiltrating. And if this is the as-built or as current conditions are, then the design engineer is presented with, how do I get water out of here, given that there's no way in hell that anybody's going to give me a permit or allow me to bury those houses in 6 feet of concrete stabilized, cement stabilized soil, because people in Texas don't like to go downstairs to get into their house. So this would be a good candidate for some sort of relief sewer, if you will. Provide a hydraulic connection to get water out of here to go to somewhere that it's permitted. So that's one of the uses of a quasi 2D model. Another use is to look at the actual flow directions. So to do that for visualization, we want to put arrows on it. Everybody loves fancy arrows. And let's make them big so that we, okay, this should make us really nauseous when I run the animation. So we're setting the animation up, and you can see the flow arrows initially, and I'm thinking down here we might get some direction changes. So when we run our simulation, nothing happens because it didn't take the input. Let's try that again. We look at the flow arrows, and there's nothing particularly interesting going on. Where it does get interesting is when the arrows start changing direction. I actually don't think they're going to do it because we would have seen it by now. But these flow arrow diagrams can be used to help guide both design and interpretation on which way flow is going. For instance, there's an interesting feature right here. This storage unit and that storage unit are different than the relationship of almost every other one in that there's no horizontal connection. If we load in the background map, I'll show you why. There is a pond right there, and it made no sense hydraulically to allow such a connection to occur when this particular model was being built. Now, this is a very crude ICPR model of such an area, but it does convey the necessary ideas. So let me go ahead and stop animating, and I'm going to save this model, and I'm going to open. I just said yes. We'll go ahead and we'll repeat it where that relief sewer has been installed. Of course, you couldn't find it because you didn't look for it. So you can say stuff like that to a computer, and it never goes to your boss and says that you're rude. Same study area, only in this case, unless I've got the input file wrong, this should have a relief sewer in it. It does not. Those are identical input files, I bet. We'll let it run. Oh, I bet in that prior case, this sewer wasn't connected, nor was that one. And these two have been added to change the flow. And for fun, I'll create a project like this so that you all can do something like this. I'll pick a different location. I have one in mind if I can find all the data files. The hard part will be deciding on your grid and getting the elevations. The rest is pretty straightforward. So we've now run the simulation. Let me look at my flow depths. Run the animator. Yeah, this still doesn't have a, let's go ahead and put in a sewer because it's going to offend my sensibility. Do good engineering, and there's my sewer. Let's make it, yeah, we'll leave it at 1 foot, and that's like 280. Another 200 is 560. I'll make it a 600-foot long sewer. It's pretty long for a 1 foot diameter sewer, but we'll go with that. Rerun my simulation, and we should be able to keep that cell. It may not stay below the 1 foot level, but we'll be able to dry it out after our storm has passed through. And that's how you use these two-dimensional ICPR concept models. Oh, perfect timing. We'll be done in 3 minutes, and I'll be out of time in 3 minutes. So now when we add the sewer, our deal had better be draining. Let me go ahead and see if it's actually connected. Negative flow, I actually brought water into it. That was stupid. There's a 3 foot drop, so it is trying to get into that sewer system. It's not draining nearly to my satisfaction. So again, because it's a model, you can do things like this. Let me delete it, choose yes. And let's make an 800-foot sewer, and I'm just gonna go straight to there because I have infinite money and it's a computer program anyway. I'm guessing that distance is 800 feet. We'll let her run. Here I am going, come on, hurry up. But it is doing two-dimensional modeling for me, so I guess I have to be patient. Because you can imagine doing that on a piece of paper. Yeah, I couldn't either. So back in the olden days, we just built stuff and hope it didn't break. Now we have these fabulous machines that let us talk ourselves out of doing stuff that needs to be done. I want that too. I do not know why that thing will not drain. $133 going to $122, 10-foot drop. Well, I'm not going to fuss with it on your time. My next step would be to put an inlet offset on that to guarantee that I can get water into that underground release sewer that I've just drawn there. And I have no idea if it pokes up above the ground surface out here because I don't have these elevations rendered. Oh, good, it got all drained the way I wanted it to. So now if we were to look at our flow depth, it gets kind of deep and then eventually it drains out and gets all nice and dry. And that would be something we would want to achieve. Now we might not be super happy because 4.5 feet deep in a subdivision cell that anything above a foot we consider flooding, and maybe at 1.5 feet we're actually getting to the finished floor elevations of the residences. So that's going to put 3 feet of water in their houses. They're going to be unhappy. So short of sending out a team of disappearing agents to Men in Black them every time it floods, a little flashy thing, that particular release sewer is not a very effective one. And you wouldn't put a 1-foot sewer 800 foot long anyway. That would be stupid. You do something like 2 feet or 4 feet. And I bet a 4-foot would drain that really good. We'll save that for next time. That's all I have for today. We've just demonstrated the concept of interconnected pond routing in our swim model here. The ponds are the storage units that are used to represent each of these cells. Let me go ahead and load back in the backdrop so I can do my conclusion and it makes sense. So the ponds are each of those red squares. Each of the black squares that are located mostly in the upper left-hand corner of each red square, but not in every single case. Those are the drainage areas that happen to coincide physically with the same area as the storage cell. Each of the links is an overland flow link, either what we call a backyard or a street and ditch, or there's a few other geometries there. The ordinary nodes, which I haven't discussed yet, are used in this case to connect underground sewers. And we have intentionally offset them so that we can see them in the interface. And we are having a dual drainage system. And so we now can resolve approximate east-west, north-south flow directions, as well as keep track of water surface elevations in the overland component of our model, in addition to the water surface elevations in the ditch that we would normally do it. And so that's the ICPR method in a nutshell. It's actually, it's quite elegant. It's not lost on me, and it's not lost on you, that the initial build of this is a bit of a nuisance, because you have to locate these things in drawing world in a fashion that you can actually see them. And then, sad but true, somebody went through from a topographic map, got that latitude and longitude location, found out it was 149.25 feet, and entered it into the input file. Then moved to the next one, entered it into the input file. Then moved to the next one, entered it into the input file. It's not hard to do. It's tedious. It's probably on something like that. That's got 106 cells in it. It's probably an hour's work. But by the end of that hour, you're ready to chew your arms off in hopes that you can get away from the computer. And once the tedious work is done, then you leverage the heck out of the model. All right, I am going to end the show for tonight. Thank you for your attention. I have this saved, and those files are accessible to you if you so wish on the in the lesson 17 subdirectory data in lecture. And we were looking at Woodlands case study, no relief sewer, and relief sewer. We didn't get to the Marcia Sharp Freeway. We'll do that next time. All right. If there are no questions, I also opened the uploader for exercise 1 up until Friday in case somebody hasn't got their stuff uploaded, or if you want to modify it. I'm not telling you to do extra work. If you've already uploaded your stuff, be done with it. But if you haven't, or if there's stuff that you wanted to do, I reopened it for a couple days. All right, no questions. I will stop sharing, and I will end the call and say good night, everybody. Friday is your 1 day of spring break. Enjoy the hell out of it.
I have a lot of work.
Huh?
I won't enjoy it because I have a lot of work.
Yeah, are you going down to Junction, or has that been delayed?
That'll be Easter weekend, but with reports and stuff.
Yeah, I'm going to Junction for a different reason. I'm avoiding the Hums house as long as possible, but I know it's going to crop up and I'll have to get back to it. Anyway, everybody have a great weekend. Enjoy your 1 day of spring break. And actually take the spring break. Don't say, oh, I got an extra day to do work. You know, at least blow off work for 1 day, because the gods of vacations want you to do that. That's something a professor has never ever said before, but take your day. You deserve it. Bye-bye.
Bye.